Log on, tune in, find out. Another good idea from Cambridge.
Exciting.
So everyone can read, so title is there and you can start.
Okay, thank you, Gary. So thank you very much to Basher and to Sergey for making this happen and inviting me to speak here. Being the penultimate speaker in this conference allowed me a lot of time to reflect about my slides, and I spent agonising hours thinking about how I should modify them to try and complement what other people have done. And after several days of thinking, I added the words School of Pharmacy here on my slide. Because I really want to make clear the fact that I'm not a statistician. The other thing... well, there's 2 hours in modelling, but there's only one in models. But the other thing I thought I'd bring up here is this diagram here, which you can't see at the top here. But ironically, this diagram is actually the surface of the determinant of the information matrix for a model which has clearance and K as the parameterization. And just by chance, as we discussed it before today, and one thing we see is, and you can have to trust me on this one because you can't see it from where you are, is there are multiple peaks which are very, very high, and they're almost indistinguishable from each other. And so your search algorithm has to be pretty robust to be able to guarantee you get to the right peak at the right time. So the clearance and K parameterization, it turns out, happens to be not a particularly good one, but it's fine for estimation, but for design it's a hard one. Otherwise it just looks like a butterfly. It's on me because it looks like a butterfly because my... So, on to the talk. So I'm going to talk about clinical pharmacology and people have talked about this before, but I need to put some context onto it. So in Tim's slide, this is what we call phase 4. Phase 4 says the drug's marketed. How does the drug work in actual patients? That's what we want to know. And the things that are of interest to us, how quickly does the drug work? How much magnitude of effect do you expect to get, and how quick and how long do the drug actions last for? And these are the 3 things we really want to know. Models of the time course of drug effects are generally constructed to be biologically plausible, which means the fact that they contain features which we like, and therefore they tend to be nonlinear in the parameters. From our perspective, they're linear models. Pharmacokinetics says that linearity is only based on dose. 99% of all drugs have a linear dose-concentration relationship, and therefore they are linear from our perspective. Double the dose, double the concentration. But of course they're nonlinear in a statistical sense. They have medium dimensionality, typically in the order of 5 to 20 parameters, so they're not particularly big models. We have bigger ones, but these are the most ones we deal with. And they contain random effects to account for patients being different. So this is my take on PK/PD. A lot of people talk about pharmacokinetics and pharmacodynamics separately. To me, they're part of the same system. In actual fact, PK in the absence of PD is irrelevant. All we're interested in is the effect of the drug. It doesn't really matter what the concentration is doing. And the reason why, and Tim showed this actually, and if I'd known Tim's talk beforehand, I would have chosen a different slide. PK, concentration, take the drug, it goes up and it goes down. PD, when the concentration increases, the effect increases, but due to the law of mass action, receptors combining with the drug going on-off situation, and reversible means the fact that you get a law of diminishing returns. So here, if you increase the concentration by 2-fold, you do not get a 2-fold increase in effect. But what we're interested in is that effect going to this axis and this thing here going to this axis here, so we get the time course of effects of the drug, which is all we're interested in really. And PK, the purpose of PK therefore is to put time on this axis. That's anything else is just a nuance really. Okay, so if we have the example here, if this was pain and like a headache, and you're going to take a dose of paracetamol, you want to know how quickly is it going to work, how much effect you're going to get from it, and how long it's going to work for. That's what we're interested. That's what the person who's taking the drug wants to know. That's what the mother of the child at 1 o'clock in the morning wants to know. That's what it's about, not what the clearance is, etc. But we need to know clearance to know this. So this is a slide with just to show you the fact that I use theta for my parameters. We're going to have Y as the data points, and the subscripts I and J have no more than 2 subscripts. So there's a data for the model, a model for the data, and a model for why people are different from each other. And essentially that's the only 2 things we introduce. So I had this slide because I wasn't sure how much we'd talk about this. Logically, on the last day, we would talk about it a lot. My talk could have been really only 10 minutes long, I suspect. So the Fisher information matrix was described for nonlinear mixed effects models by France in '97. And I've originally had in the slide here was first described, but I changed it, just took first out because I believe it's the first, but I have no idea really. I don't know literature from other areas, etc. Various extensions next 2 to 5 years, so all the big work happened next 2 to 5 years. And after that, after about 2003, now we're playing around, we're trying to make it work. So really all the first bits of trying to define the matrix, there's some new stuff, of course, of FOCE, which is linearized at the mode, etc., and stuff like that, but that's new now. But all the big work happened in the first 2 to 5 years after that. There's a whole bunch of different methods to accommodate for parameter uncertainty, and they always have multiple letter acronyms. In our work, pharmacology, we concentrate particularly on the determinant and related criteria. We tend not to use A optimality.
Can you read these acronyms?
Oh yes, this is ED, EID, API, HCRND. You want me to tell you what they are as well? Okay. Okay, this is the E is this expectation. So this expectation of the determinant over the prior of your parameter space. And this is expectation of the inverse of the determinant. And I can't remember what API stands for, but essentially it's the negative expectation over the natural log of the determinant.
Is and what Luke runs up at the
yes, it is. What's the API stand for? Remember? I just can't remember. I know it, but I just can't remember at the moment. And this is basically where we're taking a fixed points. This is just a hypercube over the natural log of the determinant. So instead of doing a whole prior distribution of thousands of samples, you just take two, one on either side of where you think it's going to be symmetric around perhaps the parameter of interest, the value of interest. That's okay. I'm happy to read that. Okay, and that we know that, of course. There's lots of population software, these ones here. I put them in random order. And the PK stamp should be on here as well, I apologise. In the majority of times, I'm going to concentrate on blood sampling times here, when to take the blood samples. Clearly, you can optimise on any controllable design variable. We'll just talk about blood sampling times at the moment. Basically, the clinical environment is uncontrolled. It's very difficult to get controlled. You remind yourself in the clinical environment the fact that the people who do this are not there to do studies. They're to look after patients. Your study is the lowest priority in their life after having a cup of tea. Then they might think about doing something for your study. So it has to work for them, otherwise it's not going to happen at all. So in an outpatient situation, the patient comes in at some unknown time, unknown to us until they get there. They arrive there, they spend 1 hour in a clinic and they go home again. You can't optimise for a time for that very easily. Emergency room, somebody might be about to take a blood sample, somebody else comes in, their arm's fallen off, they're going to get priority over your blood sample. So it's impossible. Sorry? Well, that's right. If they were on the drug in question, that would be fine. Okay. So it's impossible for designs to be conducted exactly per protocol. And this leads to unplanned suboptimality, which therefore dictates the performance of the design. So your design was now going to be dependent on somebody else's problems. When in actual fact, the unplanned suboptimality is where many studies fail. So the Tim's example, where he had a biologist who had done this before and had magically made a good design, actually is not uncommon. Some clinicians are extremely good designs. Other clinicians are doing this because they're doing it and this is not part of what they want to do, and they do extremely poor designs, so poor that you can't actually analyse their data with anything other than like a simple linear one parameter model perhaps. So sampling windows, therefore, are a way in which we can have planned suboptimality. We know it's going to happen, so let's plan for it rather than use their choice. So efficiency has been defined here, and it's been defined at least 4 times in the last 2 days. So we're just defining it now as the ratio of the determinants. This is the best design, the optimal design. This is the current design, and the ratio to the power of 1 over p. This will give us an efficiency, which will be less than 1. We pre-specify some level of efficiency, say like 0.9, and say, well, I want all of my designs to be 90% as efficient as my optimal design, and from that I intend to create a window of opportunity to sample. And therefore, essentially, I want all of my sampling times, or my design variable, which is in some window, to be efficiency of greater than 90% or 0.9. And I've just defined here, although we can relax this later, defined here the fact that sampling windows, this must be bigger than that. And we also believe the fact that this one here should be bigger than the upper end of the last window. But we can relax that, it's not a requirement for the process. The issue, of course, is, as with all things, it's great. There's no analytical solution. If there were analytical solutions, we'd have much shorter conferences. So nonlinear models are the bread and butter of good conferences in my mind. I'm going to talk very briefly about this because if you haven't covered about sampling windows before, there's a lot of really good work happening here and has happened before, and we're really just building on behalf of that. So there are basically 4 methods which have been used before to try and work through this problem. You've seen this slide like this before, actually. I think that Tobias showed a slide like that. This is just the standardized variance here, and it peaks at the optimal sampling times, etc. And this is logical. It's a great idea. And actually, if you had a single patient, this would work extremely well. And you could then just index your lambda p here to be something which has a particular efficiency of interest, and that would be it. But unfortunately, the fact that you would require an assumption of independence for this to be, the fact that the blood sample is within a patient versus between patients, etc. So you really then have to have one of these for every single patient, I suppose, and then sum them up over that surface. Other approaches that the Leon Ahrens' group and Gordon Graham has been involved in this, and Kay as well, etc. So what their idea was, and it's another excellent concept, is the fact that we estimate both the time point, the de-optimal time point, and then some delta value, and estimate the value of the delta value around that. And then you can get the windows at the same time as you get your optimal the sampling point. I mean, that's nice. The difference, of course, is the plus and minus here implies a symmetry. You could take it in the log domain if you wish to, and then enforce asymmetry, but once again, that these are assumptions which are difficult to know what they're going to mean. Another possibility, which I think this is Kay's one, came up with the idea of just, define all your windows up front and search across them. Get a whole bunch of windows, then choose which one of those windows seem to give you the best possible responses, which is a good idea. It assumes the fact that you've produced a set of windows initially which are going to do the job. The marginal one, this is like the profile likelihood. We saw that the other day. Doug Bates described this in terms of an estimation framework, but there's no reason why you couldn't do this in a design framework. Fix all your design points and then vary one until the efficiency changed. It's actually quite trivial. It's been used quite a lot. The problem is the fact that it's pretty optimistic because it destroys the interaction between the sampling times, and essentially you've gone back to square one again. So there's no gain, but you do get some feeling for this. We did a little bit of work in a fully Bayesian framework. We did a Bayesian design scenario, and in this case here, it was adaptive. So we actually conditioned the sampling window for the second sample on the first sample having been taken, and then worked out from that one. But that was in a fully Bayesian framework, which is slightly different, and it was only for a fixed effects model as well. So therefore, it had no between subject random effects in it. So the aim of this work here was to develop and assess a method for determining sampling windows that could be applied to population PK studies. Actually, it could be PK-PD, or it could be anything like that. So essentially, it really could be any nonlinear mixed effects model, I guess. There's no reason why it has to be pharmacokinetics. So an exact solution for sampling windows exists for the case where there's only a single sample. So that's all we need to do now is create that situation. So if you've got a single sample, you can exactly calculate the window, which is going to give you 90% efficiency. So a simple solution, therefore, is to recast the problem into which there is a window, for which the window for any given time point is considered as if all the other time points were known and fixed. And if you do that, then you can exactly calculate them out. Now we're going to try and think how we're going to make this work. So if we have a design in the range of the low to high values of time, I'm just using time again, and there's a de-optimal design which exists within that range, which I've said there are K samples, and these are all the de-optimal samples. And I can determine the sampling window for the first time point with an efficiency of greater than the symbol. And the first sampling window can be calculated analytically just by setting the subsequent sampling times to their d-optimal times and saying all the sample times are taking exactly the d-optimal and just vary the first one. It's like a marginal window. So the sampling window is just the value of A1 and B1, which guarantees that psi here, or psi of psi, our criterion, is going to be greater than our efficiency, and conditioned, if you wish, that the 2 to k are all at the optimal time points.
Just for understanding, when you say you have window, so your point, actual point, could be at any
Yes. Any point within the time frame.
point with equal probability or what? Because it could be different things.
We'll get onto the distribution of the likely time points soon, but at this stage, yes, equal probability. So essentially, the PK curve goes up like that, and you've got a window here, and the sample can be taken with equal probability any time from that period of time. So actually,
given that the FIM is just an approximation, how do you calculate it analytically?
I mean, this is a graphical example. Analytically, at this stage, it was done by a search. Just basically, you can either fit a curve. This is just the efficiency here. This is the 90% mark here. Here's A1 and B1. This is the optimal time point here for this one here. I mean, in this case, if we did a search, I expect that we would be able to easily solve this analytically if we sat down and had time to do so. So for a single window, you can exactly calculate the values of A1 and B1. I think so. But anyway, so the second sampling time then, so what we need to do now is think about, so the second sampling time we need to think about, I now have a first sampling window, so I'm going to generate a pseudo data item, which I'm going to call T1 with a tilde above it, from this window, and I'm going to treat that as if it was a real data item. Now I'm going to calculate the window for T2, conditional on T3 through TK at the d-optimal time points. And then I'm going to then calculate out the sampling window for 2, given that I now have a pseudo data item and 2 d-optimal time points left, or a k minus 2 d-optimal time points left. So I'm going to do this lots of times. So this is going to be recursive in nature. This is the nth iteration.
For the third through the kth, you're taking what would have been the optimum to begin with, or you're recalculating it based on that original?
No. On each iteration, well, I'll go for this slide here if you like, and this will hopefully might make it clear. I don't know. I'll come back to that point. But so basically, what I have now is I have k sampling windows, which are given by boundaries A1, B1, etc. out to k. This is the nth iteration in this notation here. I'm going to generate T1 for nth plus 1 iteration from some distribution from this here, which I can calculate out, conditioned upon, seems to have, fortunately I bought a spare. Right.
You're becoming a statistician.
I don't have transparency though. Okay, so this is my spare, which I have in my bag. So therefore, this one here now gets generated from this, given the previous pseudo data items I've generated. The next one gets generated based on this one up here, and the remaining ones that to be generated on this iteration. This goes through. This churns over. It's just a standard.
These aren't what really happened then?
No. These are just possible realizations of what could happen. This is these are pseudo data, and from this we're going to get a pre-posterior.
But there is some kind of feedback. So if I know already times where observations were made, I can easily amend optimal design and to send a message to the guy who is doing this design.
No,
it's logistically impossible, but let's assume it's possible. And then actually the targeted point will depend upon, so you have to find out optimal amendment to optimal design, and then distribution of next time will depend upon what your practitioner can see.
So what you say, we did that first. This is the idea of an adaptive. So therefore what they do is they on their iPhone app, they dial on the time they took and then calculates out the window for the next time. We as an idea, it's a thought experiment, we did that. But this is one we want to do everything up front, so it's a static design, and we intend to go through and then run the experiment as if it had gone through many thousands of times to determine what would happen. So I'll show you how this works out. So here's our model. I also changed the name here because I had a one-compartment model up here, and I know this causes a lot of stress here. So I called this a 3-parameter bi-exponential model because I felt that was less risky. I can tell you why pharmacokinetics is called a one-compartment model, because we only count the number of disposition compartments. We don't care about input. Once the drug's in the body, the drug, doesn't matter how you get it there, will have exactly the same disposition profile. And you might get it there by oral or by injection or by putting a patch on your arm or chewing gum. Doesn't worry. This how many disposition compartments you have. It's the reason why we don't count the input compartment. Just in case you're always worried about that. So there's parameters here, Ka, K, and V, and K is the ratio of clearance over volume, and this is the stuff. There's a proportional and an additive component to the model. I think there's probably a mistake in that slide as well, so I won't stay on it too long. So here's our initial samples, Kasai naught, this one here, these are the optimal time points, which were these numbers here. So iteration 1, I'm going to go for it again in this particular example. The sampling window there is going to be calculated out given that the second two were taken at exactly 3.46 and 12.63. Once I do that, I generate a value, a pseudo data item from the window I've just got from a uniform distribution. So I'm assuming there's no increased probability at either end of the distribution. It's just uniform over that range. And then from this one here, if I know that one there and I know this one here, I can calculate the sampling window for this one here. And then I generate a data item of that from this distribution here. And then I can calculate out the third sampling window based on knowing the previous two, and so forth. And it will go through. I'm not going to show you that 2,000 times because my talk would be too long then. But I've done this, I pre-prepared this to show you how it would look. So therefore, this then is very simply compute some pre-posterior means of the sampling windows, because essentially the lower bound is just the mean of all the A1s, all the 2,000 iterations of A1. The upper bound of the first sampling window is the mean of those ones there, etc. That's not So here's some trace plots to show you what happens if you do this lots and lots of times. So this is A1, B1, and there's really not much to see here, I suppose, except this one here seems to be concentrating around this region here with some spikes up to about 0.6 hours. This one here is concentrating around this region here with some spikes down to about 0.5 hours. It's not required that these windows don't overlap. They're allowed to do what they want to. They can find the natural solutions. So sampling window 1, these times here are the first time, second time, and it seems that they are quite well defined in that circumstance. So looking at autocorrelation, because this is a recursive MCMC process, we need to think about, well, how conditioned is on our initial estimate? I mean, if we put something else in, would it be affected? And if anybody's done any sort of MCMC processes, these autocorrelations are remarkable in the sense they go away almost immediately. When you do estimation, they usually hang around forever and they're a pain. But in other words, they are generating essentially independent samples over the time. So the 90% efficiency sampling windows were these windows here around this time here. You can see A, the fact that they are asymmetric. You can see B, the fact that they're time sensitive. So this window here is bigger than this window here, etc. This is what you expect to see. There's nothing remarkable about this. So this is Lee, my PhD student, drew this, and I thought it was nice, so I decided to put it up in the slide. And it's really hard to interpret, I must admit, but I still quite like it though, to be fair. This is like a floating egg in space. This is the first sampling time, second sampling time, third sampling time, so you can now work out that the sampling time, any samples that occur within this egg here will be 90% efficient if you wish. This is based on a enumeration of a single iteration. It's not the final solution for this. It's just to conceptually show you what you'll be looking at. So we need to check for convergence because this is a numerical process. So we just essentially run two chains from what we would call over-dispersed starting points. And if you notice the fact that these points here aren't necessary from the windows either. The first point, of course, is ignored. So that's the reason why we didn't bother, like 0.59 is never used, because you just condition on the second two times and you might create a window for the first time. So the fact that it's the same number makes no difference in this circumstance. So you run two chains starting from these starting points for 2,000 iterations, and then you do this plot here. This means something. It doesn't mean anything to me. They look like fuzzy caterpillars, which is a good thing. But they seem to be mixing, which is what you're looking for. So you can do these BGR plots, which are essentially like an analysis of variance. You're just comparing within and between chain variability. So when these get to 1, all very close to 1, this indicates that you've got convergence. And although these look like they don't get to 1, the scale here is like 0.995 to 1.005. These are essentially almost 1 to start off with. So it's really converged within the first 100 iterations or so. But it clearly has out here.
Steve, what you use is BGR, what type of TLA is it?
Okay, I call it blue, green, red because that's the colours you can get out if you change the colours on your screen. But it's a Jolman-Rubin value, and I'd have to ask Peter. Peter, you know what they are? This is I've got the equation on another slide.
New Zealand?
No. This is Jolman, Rubin, and
Rubin.
Gelman, Rubin.
And Brooks.
Brooks, that's it. Yes, they devised this method of determining it, and I apologise for not remembering. I have another slide on it, but I thought I wouldn't show it to you. When it goes to 1, it's converged as far as we're concerned. So, I mean, this is quite a simple talk. So, to summarise, we proposed a method for determining sampling windows for nonlinear mixed effects models. It uses an MCMC style recursive sampling approach, similar to Gibbs sampling in some sense. It's all based on pseudo data, therefore it's all pre-posterior, so it's not truly a Bayesian inference from an estimation viewpoint. At each iteration, the windows are essentially computed by exactly. They are computed to any degree of arbitrary accuracy that you wish. It's not necessary to condition the search such the windows do not overlap. They automatically solve the problem for themselves, at least in this example. And it converged rapidly and remains stable over subsequent iterations. You don't need to run it for 2000. We did that just to make sure it was going to be relatively stable over that time, so it seemed to work. I need to do 2 more things. One is I need to acknowledge Lee as my PhD student who actually did all the work while I had coffee. Because really, I just drink a lot of coffee. And James McGree, who's Lee's co-supervisor, and James is somewhere in the audience sleeping at the back there. And John Eccleston, who helped us think through the problem. And Dilbert for the use of this. And that's all I have.
So, anybody or everybody finished to read? Questions or suggestions?
Actually, yeah, it's very nice presentation, and you managed to solve a very interesting optimization problem. What I would say, you are sort of solving the inverse problem, and you can address a much simpler direct problem, if I can write on the blackboard, and that's what we implemented in our software tool in PK step. So what we do, we start with the
You have 3 minutes.
yes, we start with the optimal design. So suppose it's a single sequence then here. Then the first option, you specify this delta, the size of the window. Here, 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 and here. And then you do brute force Monte Carlo. You generate a sequence from uniform distribution in this window, point here, point here, point here, then another, and you do it n times. If the sequence has enough number of points, the matrix will be non-degenerate, so you can calculate the average design. Or you can calculate individual design, and then you can calculate average value of efficiencies or efficiency of the average matrix and compare it to the optimal. So we don't solve any optimization problem, but at the end we report if you have this size of delta, which the user may change the size of the window, the efficiency of the average design will be, say, 0.93. Or you can specify different delta for different intervals. For example, if the drug has long half-life, you will be interested to have a short or small window here, and it may be large. So we don't solve any optimization problem, but in terms of pragmatic approach, what do you think?
Okay,
I'm
so,
just
well,
curious.
I didn't show that actually. I had a slide on that, but I decided to delete the brute force method. The brute force method, which means you simulate from the windows and compute some metric, or simulate from a range from which you believe a window will exist, and compute some metric of that. We do that currently in POPT, and WinPOP does that. The reality is the fact that it's really quite inefficient. You have to generate several thousand samples, which means information matrices. And I believe this method that I've got here will be able to do this probably within maybe 200 values, depending on the complexity of the problem. The other thing which we're playing with, just as a note, is in this method here, you don't need to start with the optimal design. I did that, but it was actually distracted from my talk. In theory, I could start from any design. But that's a potential future implementation. It hasn't been done yet, but I suspect in the back of my mind that finding the optimal design, which we don't really want to know clinically, what we want to know is a design region. And the optimal design, what we normally do is a two-stage process. Get the optimal design, then work out regions in which we can take a sample, but why don't we just get the whole lot in one go? Just as a thought. But you're right, so your method works perfectly well. And in fact, that's roughly what we do in WinPOP, but it does require several thousand samples to be generated from the windows. If you've got a lot of windows, you've got a lot of independence, and when you start mixing to try and make sure that you cover the ranges appropriately. So it's really intensive, and for Tim's model, it would be impossible to do. Whereas this actually would run faster than Tim's estimation based on using the exchange algorithm, because I guess you probably did about 500 iterations in that, give or take, for the exchange, versus this one here, with 500 you would have solved the windows at the same time.
Well, in terms of running time, this is very fast, especially if you have closed form solution for your...
Oh yeah. But I was thinking about from Tim's problem, his example where he took 1 minute 47 seconds to evaluate information matrix on one occasion.
Other questions?
I'm a little confused in your update step.
Yep.
Can you go back to the slide where you were setting it up? You had the times you were going to say, yeah, that's the one there.
Okay.
Okay. So you have a window, and initially you're allowing T1 to be anywhere in the 0 to 24 range, is what I read there.
It has to be within a defined range. This is the range of whatever interval you allow it to be. But you calculate the values of A1 and B1 such as that for all values of time, your efficiency is greater than 0.9. And this is going to bring it right back to a small region of interest. And for, I think, to make it more stable, then I would condition to make sure my windows don't overlap, and therefore my sampling times are sequential.
What kind of information you deliver a practitioner? So this means.
Oh,
That's why I'm confused.
yes. Okay. So for this thing here, we would get
But after step one, so you
The practitioner would get-
observation. So what practitioner?
the practitioner will get this information here, take a sample from whatever 0.28 hours is 1.25 hours, so 20 minutes to 1.5 hours after dose, and we'd ask them to take one blood sample in that range.
So it's what you are saying to practitioners.
Yes, this is what we tell. This is the only thing we tell the practitioner, that bit there. In our studies, we've done this before using sampling windows. We get about, it's a little bit variable, but about 80% conformity to our sampling windows from a clinic situation. If you had a controlled environment, you probably get close to 95%, I guess.
And so do we give any recommendations? Should it be to the center of the
Not anytime.
You don't
Anytime.
advise anything?
No, I don't know, because essentially, if they know that, they can work out what their tea time is going to be. And when they go, no, because really people are really busy, they want to have their breaks as well, and you've really got to work around them, so you need a time which is going to be relevant. So they want to have their tea time, they want to see patients, etc. They've got an hour and a half to take one blood sample. They can do that.
But if pursue slightly different, before I start, maybe there was a question.
Yes, I have a question, right?
You have a question.
Yes, please. Yes.
Not you.
You, me, yes.
No.
Okay.
I said trouble with your eyes. What are you looking at?
Please.
When you optimized the first Windows conditioner on the fixed de-optimal time points for, leave it at that one. No,
Yep.
that one.
That one.
The one with the sampling.
That one?
No.
That one?
The one which you had
The
before.
final one.
the advice you're giving to the practitioner, I think.
Yeah.
That's an
Give
edit.
it a-
Okay, right, good.
give it a yes. When you optimize the first sampling windows, yeah, that's conditional on the fixed time points,
Yep.
last two time
Is it-
points. Yeah.
Yeah, but it's true. Yes, but at that point, it's not optimized. You're just developing one realization of a potential set of sampling windows which could exist. And this here is the average of 2,000, the lower bounds of the first sampling window, 2,000 upper bounds of the first sampling window. It doesn't have to be 2,000, it was just chosen. But so those times there are now accounting for all the pseudo possible ways in which this data could have arisen.
Okay, but when you evaluate the efficiency with that sampling windows, with that particular sampling windows, conditional on the fixed the optimal time points, the efficiency will be 90%, isn't it?
Yeah, well, that's what we're aiming for, 90%, yeah.
Because what I'm trying to say is, when you move to the next time point, do you allow the first window to change or?
No, the first window can change on every iteration, but during an iteration, the window is fixed on that iteration. Once you calculate it, that's the window. If you notice when we start with over-dispersed sampling time, so you know these are not the optimal. So when you start this run here going, you're actually starting at times which are quite a long way away from your true efficiency which you're aiming for.
Because I was thinking that if the windows are not changing, you know, if they're not changing for every step, then maybe you might not be able to assess the overall efficiency of the.
Yeah, no, for a iteration, they are fixed once you have them, but between iterations, of course, you generate more samples and calculate them again. Sorry.
I think you will continue. Yes, now.
Yeah. Thank you very much. Yes. At the very beginning, you had a derivative function for a d-optimum design.
Yes.
What is the relationship between just going down a bit from the optima and these you get here? Equivalence theorem must suggest there's some relationship, I think.
Yeah, actually, I also want to add to you. I can do it.
Shall we go back and look at the picture? How about that?
Are we talking about back here?
Somewhere at the very beginning.
Yeah.
That's it.
Right.
So these automatically give you windows, and if you just move down, you presumably calculate the efficiency.
Well, yes, you can, and I think this is. But you have to assume that everything's going to be independent. The assumption of independence is going to be critical here. Therefore, sampling time is exchangeable between people and within a person.
I still do not understand.
So in a non-mixed effects model framework, this is arguably by far the best way of doing it. This is like straight away analytical. But for a mixed effects model, where each person, so that their correlation structure, if you can't take a blood sample out of Ken and put it into me and expect it to be the same, it's going to be different.
But I still do not get it. Let's first assume what we are going to estimate. So if you're going to get better estimate for one individual, so it should be in one function. If you care about the whole population, it should be drawn another function. But I think that actually this plot and the equivalence theorem gives you what is needed to almost complete. For instance, if you know, or you just show this curve to practitioner, it should be changed a little bit curve, but we can discuss. If you show the curve, slightly modified curve, practitioner, then he will see immediately that if he moves this point from here, then on this scale, we can actually put numbers which will describe losses. So immediately, the practitioner will see, so if his point here, so he lost this, and that's all. Comparatively to the optimal design or whatever design. Because it's called with a sensitivity, usually it's called sensitivity function and so on. And because we are in the vicinity of optimal design, hopefully optimal design, then all corrections are of the second order. You can show that if you move from here on delta t, so all correction will be of delta t squared, because it's within extremum. So to building that type of curve and on this scale put numbers which reflect your losses, then you're done.
But for a mixed effects model, I just don't think you're going to be able, because you need to have independence between samples, and therefore there's lots of patients here all giving you samples.
Why do we
correlation within an individual, and here every sample now is treated exactly the same as if it was equivalent, so exchangeable between people and within people. Now, within a person, sampling times are exchangeable, but not between people, and not between groups either.
Yeah, but we can, you see, if you are talking about individual, we can plot this curve for individual. We remember it was 3 information matrices which are plotted. And we can do this for each of these information matrices and just to immediately to evaluate. Okay, we can discuss.
Yeah,
but I think that there is some kind of future for that type of approach. First of all, it's easy to read. I'm not sure about practitioner, but I'm a little bit confused with what we discussed today. Seriously, because you have this interval, you deal with this interval for practitioner, and how he will proceed? He will be confused, or she.
Well, our empirical success rate here is more than 80% with using these things. So I expect that when we do this, and I've designed, I know, many studies prospectively, and when we do this, that practitioners typically take the samples within the window. If you give them a window, if you don't give them a window, that's, if you give them a time point, this is when they get confused. But a window, they say, right, take a blood sample between 5 minutes and half an hour, whatever it is. They're actually pretty good at doing that.
Yeah, but what I have said, you have to take this point, and if you can, then keep in mind that your losses will be like that one.
But
and then
he
will make decision himself or herself. Sorry to be politically correct. And
it's not necessarily about losses here.
Sorry?
It's not necessarily about losses. The practitioner can move a little bit and actually be in a better shape compared to, because he or she enlarged the design space.
How we can enlarge this? We can say that you cannot move below this point.
So here's another little question. Did you actually sample?
We have 3 minutes.
That won't take that long.
Not you, we.
We have the rest of life. In your simulations, were you sampling from the parameters each time?
No.
So you're doing a fixed effect simulation?
Yes.
Thank you.
But that is a natural extension. That's a good point.
And what if we're doing?
Yeah.
A question related to the practice, but also to how you do the designs. In practice, at least my guess would be that most of the clinicians, when they see the window, are either going to do it as soon as possible, or they're going to suddenly find it at the end of the window and then do it. So you might have they might be very much at the end.
Mm-hmm.
Related to that, if you're on a time scale of hours, can you adjust to that and compute the new windows? It will adapt to whether or not they've moved something off of where you want.
Typically, so adaptively, anything's possible. Typically, in a clinical situation, people are going to want a fixed design, which they're going to register, and that's it. They're not going to budge from that design, so it's not going to happen. You could, what I haven't analysed as a point of interest would be to try and find when clinicians typically do take samples. Sometimes, actually, if we have replicated measurements, so we can see a support point, say arbitrarily this point here, which says you want to take 2 measurements there and 1 there, then we just tell them to take 2 samples, but not at the same time from the same window. And they're also quite happy to do that, and it's also quite successful. So yeah, clinicians, if you explain what they need to do exactly, and it's written down on a piece of paper, it's going to work. They try and help, but they're not going to go out of their way to make your work for them. But adaptive designs in an emergency room situation, etc., is just really difficult. They've got to have something on the wall which the nurse can see who's on at that moment in time.
That sign on the wall can be controlled by a computer.
It could be.
You can adjust it, and it can.
On their iPhone, they can get their iPhone out and plug it in and see what they should be doing next. Yes, anything's possible.
Yeah, okay, it's a little bit of fantasies here.
There's also an issue that if you have an optimum point, it doesn't mean that symmetrically on both sides of the optimum point you get the same efficiency.
Of course, but you can adjust, like in this simple Monte Carlo approach, you can use different, half width in
the point is that
different direction.
What you want to give to the practitioner is the opportunity to sample within a period of time and be sure that you don't lose more than a number on efficiency. And that's what you are doing. And
Okay, it's good that Pasha actually interrupted this meeting. I believe that to interrupt meeting with Pasha's comments, it's the best thing.
Why interrupting meeting? Well,
because it's break.
Now, before the break though, can I make a comment? So before the next session after the break is going to have a discussion about software. It's going to have a discussion about location of PODE for 2012, and also any free discussion about optimal design which people want to have. Any things they've been thinking about over the last 5 days, there's an opportunity to have a chat about it. So the session was essentially open, and France's talk will actually be quite a small part of that process. France has just decreased the number of slides as we speak. We're quite a small part, so there'll be plenty of time for discussion, so bring your thoughts with you. Question thoughts, that is.
Thank you.
Okay, thank you.